So our last section of chapter 12, we're doing the second part of 12.5. We're going to talk about curvature and acceleration. All right, so yesterday we did a little work to develop this idea of curvature. How do we quantify the curvature of a curve represented by a vector valued function? And we talked about the development had to do with the arc length and the arc length parameter and how those two ideas were related. What I want to talk to today, and I kind of hinted at it yesterday, I want to talk a little bit more about the geometric ideas of curvature. So we said when we came up with our expression for curvature, we said if we had curvature, if our curvature equals k, that was a symbol we used for curvature, excuse me, at some point p, we said the radius of curvature was the reciprocal, or the radius was the reciprocal of the curvature. And we're going to use a capital R for radius of curvature. Some books you'll see they'll use rho for the radius of curvature. And we said that was 1 over k. The circle, what we're gonna talk about now is a circle with radius r that's tangent to the curve at point P. And we're saying it's tangent to the curve at point P on the concave side. We call this the osculating circle. And I'll write it up just a second. I turned my thing off by accident. We call the circle the osculating circle. Or you'll also hear it called the circle of curvature. So what we have is we're just making the circle, the radius of curvature matches the radius of the circle matches the radius of curvature at a particular point on the curve, and the center of the circle is called the center of curvature. So this is just a way, it's similar to like a linear approximation where we use a line to approximate a curve. So what we're talking about here is having a circle that approximates our curve at the point P, because the curvatures are the same and the center of curvature is the same. So let me draw a picture of the osculating circle, and we can come up with a nice equation to find the center of curvature. So we have a coordinate system. We're in the plane here. So there are my x and y axes. And we have, let me draw my circle first. It'll be easier for me to draw the circle and then make the curve match that. So there's my circle. This is my osculating circle, or my circle of curvature. And we have some curve here in the plane that is going along here, and at some point their curvatures are going to match exactly. So we'll say that point is here at point P. So at point P, the curvature of the curve and the curvature of this circle are exactly the same. So they have the same radius of curvature, and this is our center of curvature. So the point here is our center of curvature. And our circle is our osculating circle, or our circle of curvature. So we want to find an expression. How do we find the center of curvature? What we're thinking of doing is at this point we can approximate the motion as circular motion, just at that particular point. And the circular motion is going to have this radius of curvature. So let's draw in a couple of vectors. We're going to draw in a vector to the center of curvature. So there's my vector to the center of curvature, and we're going to call that vector C. So that's the position vector to the center of curvature. And I'm going to draw in a vector to our point. So there's a position vector to our point P, and that vector is going to be R at whatever particular time t we're talking about here. So looking at this diagram, what vector now, what other vector quantity are we familiar with that's going to point towards the center of that circle? What? The principal unit normal vector. Our unit normal vector is going to point to the center of the circle, because at this particular point t, at that instant, we have this circular motion, and the principal unit normal vector points to the center of the circle in circular motion. And so the unit normal vector is how long? So the unit normal vector, length 1. So what's going to be the vector that's going to reach all the way to the center? If our unit normal vector is length 1, what can we multiply that unit normal vector by to get to the vector to point to the center? The r, multiplied by the radius of curvature. So I'm going to draw in that vector. That vector is going to be our radius of curvature times our principal unit normal vector. So the position vector to the center of curvature, C, from our diagram, is the position vector to the point that we're interested in, plus r times our principal unit normal vector. So the osculating circle is a circle that most closely approximates the curve at point P. So this is our expression for finding the center of curvature. And the reason that we're talking about this osculating circle is we can use the osculating circle to help us think about the geometry of the curve, how the curvature changes, what the motion is at a particular point. But we can also think about, if we're not confined to the plane, if we have something that's a particle is moving in space, we can talk about the osculating plane. The osculating plane is the plane that's defined by t and n. So we call that the osculating plane. Osculate comes from the Latin osculum, which means to kiss. So the osculating circle is the circle that's kissing the curve at that point. So they're just barely touching. The osculating plane is the plane that is the plane that's kissing the curve at that particular point. In one of the homework problems asks you to calculate what they call the binormal vector. So we calculated the binormal vector B, which was t cross n. And we decided that t and n were always in the same plane. So the binormal vector t cross n is going to be normal to the plane defined by t and n. So the binormal vector is normal to the osculating plane. And this binormal vector B is just another vector that's used to analyze curves. When we have a curve that's not in the plane, and we think of our unit normal, our unit tangent, and our binormal vector, if the curve is twisting around in space, that binormal vector is going to be changing. So the binormal vector, how that binormal vector changes gives you an idea of how the curve is twisting. So it's used to analyze what we call the torsion of a curve, and that's how it twists, how a curve twists in space. So I just wanted to talk about this osculating circle, because you'll get problems that ask you about the osculating circle and the center of curvature, because at this point we can say that we're instantaneously we have this little bit of circular motion. And if you go further in any kind of calculus related to geometry, differential geometry, what do I want to say? What's the other field that I'm thinking of? Topology. Any of those things where you're analyzing geometric shapes, you're going to talk about these binormal vectors and this curvature and the center of curvature, the osculating plane, that kind of thing. So I just wanted to kind of give you a little bit of a quick introduction to that. And if we have time at the end today, I'll show you a demo that I have that has to do with osculating circles. So our osculating circle touches the curve at this point. The curvature is the same. The curvature of the circle is the same as the curvature of our curve. The radius of curvature is the same as the radius of the circle. All right, so now after that little detour, let's go back to acceleration and curvature. So we decided, as we were talking about curvature yesterday, we decided that the curvature should have something to do with the acceleration, because the acceleration is what changes the direction of our motion. So that's what's causing the curvature, is this acceleration, the normal component of acceleration. So when we came up with an expression for the tangential and normal components of acceleration, we said that the acceleration vector, A, was the rate of change of the speed with respect to time, times our unit tangent vector, that's our tangential component of acceleration, plus this quantity that was our normal component of acceleration. And we did some analysis after this to make this easier to calculate. So this was our initial expression for the tangential and normal component of acceleration. I'm going to work a little bit with this t prime, with this normal component of acceleration, and we're going to relate this quantity to the curvature. So we know that the magnitude of t prime is the rate of change of t with respect to t. Yesterday we came up with a relationship between our unit tangent vector and our arc length. The rate of change of the tangent vector with respect to time is the rate of change of the tangent vector with respect to the arc length times the rate of change of the arc length with respect to time. And what quantity is dt ds? The magnitude of dt ds. Yes. What have we been talking about? dt ds was, that's how we define the curvature. That is the curvature. And ds dt was what quantity? Magnitude of r prime. That's our speed. So ds dt is the magnitude of r prime, which is the magnitude of the velocity. So we're going to make some substitutions. So, substituting these quantities in here for these two, I'm going to say that the magnitude of t prime equals the magnitude of the velocity times the curvature. And now I'm going to substitute that quantity in here. And for you physics people, we should get something familiar. The acceleration is the rate of change of the speed with respect to time times our unit tangent vector plus v squared magnitude times k times our unit normal vector. And how can I rewrite v squared times k? How is k related to the radius? 1 over r plus the magnitude of v squared over r times our unit normal vector. So in physics, what do you call v squared over r? That's the centripetal acceleration. So we using our idea of curvature and our idea of acceleration, we've come up with this idea that the normal component of acceleration is v squared over r, which in physics you learn is the centripetal acceleration, or the magnitude of v squared. So just another way of thinking about our acceleration and relating the acceleration to the curvature. We had an idea that the curvature should be related to the acceleration, and this is our relationship. The curvature and the radius of curvature gives us this quantity for our normal component of acceleration. If we write this expression in terms of the arc length, so just because we defined our curvature in terms of the arc length, we're going to say that we know that ds dt is the magnitude of our velocity, is our speed. So we can write that the acceleration is the second derivative of s with respect to t times t prime plus the curvature times ds dt squared times n. So this is our acceleration written in terms of the arc length parameter. So if you go further in math, if you do any kind of differential geometry, where you're using arc length to parameterize your curve, you're going to see this expression for acceleration a lot. So now we've come to our relationship between curvature and acceleration, and how the normal component of acceleration is related to our curvature. Questions on our development? So rather than going through a lot of examples of calculations, I just want to, I'm going to present, we'll put a problem on the board, and then I just want to talk through how we might go about solving the problem. I don't want to go through a lot of calculations because you guys can do the calculations. So I just want to talk about kind of the approach to the problem. So what if we had y equals x minus 1 squared plus 3. We want to find the point of maximum curvature and the limit as x approaches infinity of the curvature. So what process, we're not going to do calculation, but what process would we go about to solve this problem? What would we need to do? Find the curvature. So we want to come up with an expression for the curvature. Maximize that by first and second derivative tests. Okay? And then you have an expression for the curvature. You can find the limit as x approaches infinity for that particular expression. So that would be our analytical process. Looking at this, what's the graph of this? What's the graph of this thing going to look like? A parabola. Intuitively, where would you guess that the curvature of a parabola is the maximum? At the vertex. Intuitively we would think that the curvature is going to be maximum at the vertex. So that could guide you if you came up with a point that wasn't the vertex, that maybe you've done something wrong. What would you guess intuitively what the limit as x approaches infinity of the curvature of a parabola would be? 0. It gets flatter and flatter and flatter. It's less and less and less curved. So that could intuitively would guide you through the problem. But we would find an expression for the curvature, do the first and second derivative test to see where it's maximum, and then we can find the limit of that expression. So similarly, what if we had y equals x minus 1 cubed plus 3, and the question asks us where the curvature would be 0. So again, intuitively, what would we think here? at the inflection point. The curvature would be 0. So the graph, this graph is going to look something like this. We would guess that the curvature would be 0 at the inflection point. Where's the inflection point of this thing going to be? 1, 3, shifted up. So the inflection point of this is going to be at 1, 3. So we would guess that the curvature would be 0, 1, 3. Again, we could find the curvature. We have a process for finding the curvature of a plane, a curve written as y equals f of x. Find the curvature and see where that equals 0. Let me look at one more. So let's say we have, we're given the equation for a parabola, and we want the radius. Excuse me. We want the radius, and let's say not a parabola. Let's say we have a paraboloid. So we have this paraboloid shape. And the question asks us, and we were given some kind of equation for this paraboloid. The question asks us, what is the radius of the largest sphere that would be tangent to the vertex of this paraboloid? How would we go about solving that problem? Find the curvature at the vertex, and we want a sphere with the same curvature, and then we can find the radius of that sphere because the curvature and the radius are inversely proportional. All right. Any questions on these little kind of thought problems? The homework is mainly calculating with curvature, finding centers of curvature, that kind of thing. Since we have a little bit of time, I wanted to show you these demonstrations. So I have an osculating circle demonstration. Where is it? Oh, there it is. All right, so here's our function, and here's our osculating circle. So we just have a polynomial function here. So the circle, here's our osculating circle. The radius of the circle matches the radius of the curve here, and we can drag this along. So this part of this curve is kind of like a parabola. So just like we thought, as we go away from the vertex, the curvature gets less and less, the radius gets larger and larger. As we get closer to the vertex, the curvature is larger, the radius is smaller. Okay, we're getting close to an inflection point here. So our curvature is almost 0, and now we're on the other side of the concavity is switched, and our osculating circle is on the other side of the curve. So there's our osculating circle going along that curve. Here's a trigonometric function, and here's our osculating circle for our trigonometric function. And a nice logarithmic function. And I have one more here. Let me find it. This is an osculating circle in 3D. This one is nice. All right, so I think here's my favorite. this is a circular helix, and here's our osculating circle. So the curvature is constant, but the orientation, so our binormal vector, is changing here. So that's we have an idea that the binormal vector gives us an idea of how this curve twists. So the curvature stays constant, but the binormal vector changes. Here's an elliptical helix. So the curvature here, the curvature changes because it's an ellipse. And then we have a sine circle. So what we're looking at, if we look at this straight on, we get a circle, but here we get a sine. So the osculating circle twists around, and the radius changes. So the osculating circle and the binormal vector, they give us they're tools to help us analyze the geometry of these curves, and that, to me, that I find it really fascinating. All right. Homework. This will help your immune system. I specially designed it to boost your immune system.
So funny.
All right, there you go.